Hi, Shiwei. Yeah, I hope you guys are doing okay. So Polly is liking the quarantine, the self-induced quarantine. I don't know about you. Let me know if you like it, like Polly does. Yeah, so I mean, you probably know that Polly has this split personality that a lot of times she likes to be alone. Okay, and the internet is perfect way for she to connect to the rest of you guys. So let me just announce for week 15 and week 16 because next week is actually the last week for this course. So just to let you know ahead of time what's remaining. Okay. So this week, week 15, it will still be somewhat intensive. But if you just pay attention in the lecture and do the quizzes, you'll be okay. What might be a little bit troublesome is PA9. And from what I observed, many of you guys have discovered that if you run into trouble with the PAs, you can always go to the videos for the PAs, and that's gonna help you go through. Because in the middle of the video, you might see Polly demonstrating what to do there. Okay, so if you run into trouble doing PAs, definitely take a look there, or feel free to ask Polly. I mean, I know that I try to be responsive, but a lot of times I don't have all the time. I really wish that I have dedicated to the course. Okay, so if you care about delay, then just go to the PA videos and probably speed run it through. Okay, so PA9 is gonna be due end of week 15, and this PA9 here would definitely help if you watch the video. You will see Polly demonstrating there and explaining a little bit how TLS really work and how do you configure your server, okay, to run on TLS. Now, something extra. Next week, we do have the last exam number 4, and it's coming up on Thursday again. And this time, since all of you will be doing it over the internet, so that preparation time is gonna be longer, and there are just so many of you. It's better that we still do the ID check because previously those students taking exams online, the number is low, something like 5, 6, maybe 7. But this time, all 40 something of you will be on there. So please allow us time to check the IDs. So we'll appreciate if you can come a little bit earlier or join the session a little bit earlier, like starting from 1:05. Okay, so that's try to do that. And so that we can start the exam right on time, 1:20. Again, the detail is in exam 4. Okay. On the good side, once we're done with next week, then you're free. Okay, week 17 and 18 are entirely yours. Hey, there's something. Okay, a smiley face. That's nice. Okay. Yeah, so I guess you guys will definitely need these 2 weeks for the other courses, finals or final projects. So for week 16, it's very simple. There's just one quiz remaining, and it's during actually the end of the week. That will be Saturday. Okay, so Thursday you complete the exam. Take it easy. And by the way, I understand for many professors or many people that will need to judge you in a short amount of time. They would look at your GPAs. But your quality is something that they will see in the long term. Okay, so you don't really need to mind all that much about the exam scores. I understand, and probably won't see you differently. All right, so just a quiz, just an exam, and it's gonna end real quick in 15 minutes. We all know. All right, good. So that was the announcement today. Today is gonna be all about a routing protocol called link state routing. So we'll be opening a new chapter, chapter 5. So the first video, about 9-10 minutes, is to review again what is control plane. We know the network layer already, right? So there's control plane and data plane. So last chapter, chapter 4, is about data plane. Now we talk about the intelligence in the network layer. Okay, so here's a review. Chapter 5, network layer, the control plane. Control plane is also what Polly likes to joke about, the better half of the data plane. Now the reason for that is this. If you think about data plane, that forwarding function there, what it does is simply, right, for each incoming packet, do a table lookup. And you know what to do with the packet. Okay, so for each incoming packet, one table lookup, and that's it. There's nothing really intelligent about it. Right? The only thing the forwarding is doing just table lookup, and it's just pattern matching. But hey, we are sending all sorts of packets coming from different sources, and they're going to different destinations, right? You cannot be sending these packets to arbitrary directions and hope that they will reach the destination. No. So that table there is really where the intelligence is. That is really, okay, guiding the packets to go to the right direction, eventually reaching the destination. So the data plane, the forwarding function, although very busy, working tirelessly trying to forward packets, but it's actually simple, stupid. Intelligence is right here in the control plane. And the intelligence is implemented using these, the routing algorithms. Okay, so routing here, what I meant as a function is to find a path, okay, for a particular source to be able to send packets to a particular destination. Or to find a path so that packets belonging to a flow can flow through the network, okay, with the right amount of resources reserved. So routing algorithm there, very intelligent. Okay. So in fact, the first part of chapter 5 is going to sound a little bit like you're attending an algorithm course. So Polly will be speaking about two general routing algorithms. Okay, so they are graph algorithms. So provided a graph, okay, if you think about it, a network having machines connected by cables is a graph, right? Points connected by lines. So provided a graph, we could calculate, we could compute the shortest path from one arbitrary point to another point. So that is what the magic of the routing algorithms are. So these two general routing algorithms will be implemented on the internet as two routing protocols, OSPF and BGP. We'll talk about these routing protocols later after we finish describing the general algorithm. Now, these routing protocols are running on the traditional routers, where you have the data plane and the control plane. So the routing algorithm is running in the control plane. Okay? The control plane of each router might be communicating with the control plane of other routers, and together they complete the task of calculating routes, and in turn generating the forwarding table, and in turn install the forwarding table to the data plane, and in turn the forwarding function, okay, can be working really fast. Now, the new model of doing routing is called SDN, software-defined networking. So the one that's doing the route computation is the controller. Okay, this is also known as the what? Remote controller, because in SDN, okay, the model is slightly different. You still have the data plane doing the forwarding, but the control plane is implemented outside of the routers. Okay? In fact, powerful machines, somewhere remote. That's why these controllers are also called the remote controllers. Okay? And between the remote controllers, routing, okay, is being done where we generate the flow tables, and the CA, the control agent, now in the data plane, okay, that's taking in all these tables being transferred from the controller. Okay, in between, there's this open flow protocol. Okay, now you should know after chapter 4. So, after the control agent receiving the flow table, the flow table gets installed, and therefore the SDN routers can do, flow table lookup. Okay, do generalized forwarding. Now, the remote controller here, okay, it's actually quite general.
inside the remote controller, you could implement multiple routing algorithms, such as the one used by the traditional routing. You can also implement other routing algorithms, and in addition to all these routing algorithms that could be running simultaneously, and you pick and choose a particular route for a particular pair of source and destination. You could also actually specify preferences or specify costs, okay, or specify other functions. Okay, so SDN's remote controller, being very general, okay, is actually working like pretty much a regular computer, okay, or expensive servers. So on these SDN remote controller, okay, we run, okay, operating systems, elaborated operating systems, such as ODL or ONOS. Okay, so these are two different operating system architectures, and both have big camps of supporters. So yeah, SDN routers are made available today that both operating systems can be installed, okay, to support route computation, flexible route generation, flexible flow table generation. Okay. So these protocols, as well as these two, okay, of the technical components in chapter 5, concern the routing function, the second important function in the network layer. In the control plane, okay, we also implement some protocols that is to do this, the management. Okay, so management of the routers or the routes or the packets traveling certain routes. Okay, so those are called the ICMP. So ICMP there is to allow generation of special messages from the routers or from the host to the routers, and routers generating something back. So these are there for the network admin to sort of probe the network to find out, okay, where and what might be going wrong inside the network. SNMP. Okay, so SNMP there, the management protocol is more there continuously tracking, okay, the statistics of the network. For example, number of packets traversing a router, number of packets traversing a route, okay, number of routes on a router, and things like that, so that the network admin can know better the status of the routers, status of the routes. Okay, so again, for management purpose. Let's go real fast through 5.1, the introduction. Again, network layer, we run two major functions, forwarding and routing. Forwarding is about moving packets real fast from one router to another. Routing, however, is for each router to generate this forwarding table or flow table, or to determine the routes for the packets to move, okay, from one to another router. So in chapter 5, we focus on the control plane here. The two models, okay, for route computation are these: the traditional routing versus the SDN routing. In the traditional routing, each router implements part of these routing algorithms, and so the route computation is somewhat distributed, and the routers work collaboratively to come up with the best routes. Okay. So there's per router control plane doing the route computation. But in SDN, okay, the route computation is more centralized, running on powerful machines, and also somewhat distant from the physical routers. So centrally controlled. And this control is called the remote controller, as they are being physically distant from the router. More specifically, in traditional routing, okay, the routing algorithm is implemented and running on each of these routers, and they will be interacting with each other to generate the best routes, therefore coming up with the forwarding tables. Okay, so in the data plane, yeah, there's this forwarding table in the data plane. The control plane there runs the routing algorithm, and together they generate the forwarding table and forward it and installed in the data plane. Now, the modern routing, the SDN routing, works this way. Okay. There's going to be a remote controller there, okay, doing all the computation and then interacting with the local control agent to install these forwarding tables, or more precisely, flow tables. So router, yeah, data plane here, having these control agent, and then at the control plane, we have powerful machines running the remote controller. Remote controller interacting with the CA, setting up these flow tables.
Alright, so that was just a review. Next one is to really introduce the true routing algorithms. It's also about 10 minutes.
Now the core of chapter 5, the routing algorithms, or the routing protocols. So a good routing protocol there should be able to identify good paths or good routes from the sending host to the receiving host through this network of interconnected routers in the middle. So that is essentially trying to come up with a path. Okay? A path is a sequence of routers, one connected to another, and connecting the initial source to the final destination, okay, such that this path here is the least in cost, so we pay the least, or the delay is the shortest, or the promised bandwidth there is the highest, therefore the congestion level will be the lowest. Okay, so finding a good path, that is the goal of a good routing protocol or routing algorithm. It's also one of the top 10 problems in computer network, just like reliable data transfer, just like congestion control. In the next couple slides, Polly is going to introduce this new term called graph. A network, okay, of routers interconnected by links is a graph. So let's focus on the network in the middle here. What you see is that we have router U, router V, W, X, Y, Z. So we have a set of routers, okay, and there are 6 of them. Now between the routers, we have also links. So link UV here connects router U and router V. Similarly, UX here connects router U and router X. VX, V here, X here. Yeah, VX is the link connecting router V and router X. Link VW, connecting router V and router W. So you see, we can go over all the links defined here, and this forms the set of links interconnecting the routers. And coincidentally, a graph is also defined in a very, very similar way. A graph consists of the set of nodes and the set of edges interconnecting the nodes. So N here stands for nodes, and here, E here stands for edge. So if you consider the routers being nodes, yeah, so the set of router here is the N here. If you consider links being the edges, then E here is the set of the edges. With the set of nodes, set of edges interconnecting the nodes, we do have a graph. So a network here is also a graph. And such an abstraction is really, really convenient later on when we're introducing the algorithm. It could also be useful when we're talking about other kinds of networks. So for example, in the application layer, chapter 2, for P2P, okay, you see there, okay, there are peer here, there, all around the internet. And we establish connections between the peers, right? So we could do what? P2P communication. So if you consider each of these peer as a node, and these TCP connections, now the core of chapter 5, the routing algorithm, is like entirely, and knows all the need to know traffic level. You could also set it simply to a constant, such as 1. Every link costs the same, 1. Okay. So that is link cost. Now the cost of a pass, is essentially also very simple. From the source x1 to the destination xp, it's the sum, of all the link costs connecting from the source to each of the routers along the path, all the way till the destination. So it's the sum of the costs from the source to the first hub router, x2, c, x1, x2, plus c, the first router to the second router, x2, x3. And so on and so forth until the last router, xp minus 1, to the final destination. So let me use an example. Let's say traversing from U to Z, and we take this path. The cost of the path will then be adding 2 to 3 to 5, and that will be 10 here. goal of routing algorithm is essentially to find the least cost path, okay, between a pair of nodes, okay, from source to destination. In Poly, we'll be introducing two routing algorithms next. First is called the link state algorithm, second, distance vector. The link state routing works this way. Inside the network, each router, okay, in the router, it implements an algorithm. Before this algorithm can be triggered, the router needs to wait to have the complete topology and link cost information. What I meant by complete topology is this. Each router will need to know N, the set of routers composing the network. E, the set of links interconnecting all these routers in the network. And link costs of all the links, okay, connecting the routers in the network. So each router needs to know how the network looks like globally before the routing algorithm can be triggered. Another characteristic is this. The link state routing algorithm will run in just one pass. So provided global information of the network, trigger routing, route computes, and completes. As a result, each router not only knows the best route to all possible destinations, it actually knows, okay, all the best routes from arbitrary source in the network to arbitrary destination in the network. So the router there, very informative, knows how the network is like entirely and knows all the paths, okay, for all the possible destinations and source pairs. On the contrary, in distance vector, routers no longer require global information. The routers also do not do one-pass route computation. Rather, the router only needs local information, namely, a router only needs to know how it's physically connected to the immediate neighboring routers and the link cost to the neighboring routers. And that's all. The route computation begins. With very minimum information, the computation gives you suboptimum results. Okay, so each router there, after running the distance vector algorithm, will know just slightly better than, nothing. And that information is definitely not quite good enough to give us the least cost paths. So what distance vector routing does is there. Each router will then, after some initial computation, exchange the result of the computation to the neighboring routers. Neighboring routers would also exchange what they know slightly better to the router here. Now, this router in the middle, after receiving slightly better information from the neighboring routers, can recompute and see if even better paths have been discovered. So if the router again discover, better paths, then tell the good news to the neighbors. Similarly, the neighbors would also tell slightly more information to the router. Okay? As such exchange expand, gradually traveling through the network. Okay? All the routers in the end learned about converge to the least cost path. Okay? So, the process you see, computation, exchange, computation again, exchange again, computation yet again, exchange yet again. So the process is very iterative. It's going to take some time, but eventually, as the information propagates through the network, everyone converges to the least cost path. So a very different model of doing route computation. Link state routing being global, distance vector routing being local. Now, another way of classifying the routing algorithms is this, by judging at how the routes are being updated. Static routing is not updating the routes. So this is only for the network that is not changing frequently. And we know that this kind of network doesn't really exist these days. So all the routing algorithms that we're introducing are working this way, dynamic. That is also saying that routes can change, link costs can change, Okay, routers could suddenly be dead and then or suddenly being booted up. Okay, so we'll try to update these routes, repeat the computation, okay, periodically, or okay, in case we detect there's a link cost change or no change, okay, or some other changes.
Alright, this time it's on the misclick. Sorry that you need to hear about the goal of routing is to find the shortest least cost path. Again, 2 times. And therefore, starting from now, we talk about the link state routing, the global routing algorithm. So the first video is to introduce the algorithm. It's a pseudocode, so it would sound like cryptic, but no worry. The next video will show an example, and right after the example, we'll take a couple quiz and to walk a problem through yourself.
Let me introduce these notations before I bring up the pseudocode for the Dijkstra algorithm. First is CAB. This is the cost of the link connecting router A and B. You should know already. Yeah. What's a little bit surprising to you is this. The cost, CAB, could be infinite, okay, because there's no direct link connecting the two routers, and therefore the cost is infinite. Second notation is this, DD. Okay, small d here is indicating that for a particular destination, the path from this router doing the computation to this destination, what is the cost of the path currently? So capital D here actually stands for distance. This is also saying what is the current distance to a particular destination D for this router doing the computation. Now, PD here, D again is the destination, okay? And PD is to indicate for this router to reach the destination D, okay, along all the routers on the path. What is the previous router before reaching D? Okay, so predecessor node along the path until reaching D. And prime is the set of nodes whose least cost is already known. So here's the pseudocode of the Dijkstra algorithm. There are two phases, the initialization phase and the looping phase. A looping phase looks really complicated, so let's not worry about that part yet and focus on the easier part, the initialization phase. So what we're doing first is to initialize the n prime, the set of nodes we know already the best route to. And we're quickly including A. The reason is this. Whenever we execute once the Dijkstra algorithm, we give also the source of the path. So A here is the source of the path we're trying to discover. In fact, after running through a Dijkstra algorithm, we will discover, okay, the shortest path to every other node in the network. Now the source, in case A is also its destination, hey, it's trivial, isn't it? We just don't send it down. Send it to 127.0.0.1, the IP address for the local host. So we can initialize n prime to just the source node safely. Second thing we do is actually a for loop here. Okay, inside the for loop, we'll go through all the nodes, okay, in the network other than the source. So all other nodes, okay, and for each node, okay, B, we check whether it's directly connected to the source. If it does, we've discovered a way to go to this particular destination, isn't it? And the distance to it is the link cost between node A and node B. Now, if the node is not adjacent to A, then it's going to trigger this line here. No route has been discovered yet to this destination B. Therefore, distance to the destination infinite. Okay. Now, from the description, you probably also see, in order to find all pair shortest path, you need to repeat the Dijkstra algorithm, providing a different source address. Okay. Now the exciting part, the looping phase. It looks a bit complicated, but if you focus first here, okay, the loop is going to go until all the nodes are in the M prime set. That is also saying that the loop is going to go until all the shortest paths have been discovered. Okay, the shortest paths to all the nodes have been discovered. And you probably guess that, hey, one of the things that will be changing in the loop is the M prime set. Okay. Yeah, indeed. Okay, the first part in the loop is exactly to do that. We are gradually adding nodes into the M prime set. Okay, and the node we pick to add is this. Okay, the node such that the distance to it is currently the minimum. Because adding this I to M prime set is also saying that the best route to I is already discovered. Okay, so why is the minimum DI here is suggesting that the best route? This is also the shortest distance to I. Now, think. Originally, okay, we have A in the M prime set. Okay, the D, B there existing with significant values are these. The nodes directly connected to the source. And therefore, the distance to each of these nodes, okay, is the link cost. Now, in the loop, okay, the first two lines here is going to include what? The node with the smallest link cost to the source into the M prime set. Is that making sense? Is the shortest distance, okay, to that particular node exactly that? Is there a way to discover another path to that node that is going to be lower than the link cost between A and I? Not possible, right? Because all the other links cost is higher. If there exists another path to I, the cost is definitely going to be longer than this because all the other link costs are higher already. Okay? So di here is indeed the minimum, and I here we've already discovered the shortest path. So it's safe to include it into M prime in fact. Now, having added I to the M prime set, this is also saying that we already discovered the shortest path to I, and the shortest distance is di. So I know there is something really nice to exploit. Okay? Through I, we can potentially discover shorter paths to other nodes. Okay? We have not yet discovered the shortest path. Okay? So what we're doing here next is to go over for all J nodes that are directly connected to I. So for all the neighbors of I and not yet in M prime. So all the neighbors of I that we have not yet discovered the shortest path, then we update dj. Okay, and that is what this formula is saying. Okay. So the new dj is the minimum of the two, the existing dj and okay, the distance to go from j directly to I and di. So the shortest distance from I to the source. So di plus Cij. So this is what the comment is saying. The new cost to j is either the all cost to j or the shortest path to I plus the link cost from I to j. So what we're doing there is to update dj. Okay, if there's a shorter path, that's just editing. If there's a shorter path, that's override the bad path. Okay, things like that. So you see. What we're doing in the looping phase is actually not much different from what we're doing in the initialization phase. So this part of the looping actually corresponds to this part of the initialization, isn't it? Okay, including nodes that we know for sure. Okay, what is the shortest path? And then here actually corresponds to this. Okay, try to discover the shortest path possible. Okay, by updating. Based on the information that is known.
Oh wow. So you guys are answering quiz 34 already. So you guys are really good at reading the pseudocode, I guess. But we still have an example to go, so that's just
That was the walkthrough of the pseudocode. I know it might appear a bit fuzzy to you. Let's go over a concrete example. So in the example, again, we have 6 routers and there are links. Each link comes with a cost. And let's assume U is the source and Dijkstra is going to do the computation starting from U. Now, the initialization phase says that to include the source into the M prime. Therefore, we see U here appearing in M prime. Next thing is to go over all other nodes. So X, W, V, Y, Z. Those who are adjacent to U, then we set the minimum distance to it, set the predecessor to rigid. Otherwise, if they are not directly adjacent to U, set the distance to infinite. So for Y and Z, we'll see, okay, this should be infinite. And for VWX, V, the distance to V should be what? The link cost between the source and V. So between U, V, link cost 7. So 7 should appear here. The predecessor for such a path definitely going to be A, because we just added A to the M prime set, right? And we're reaching V through a direct link. Therefore, the previous node must be the source, U. For W, link cost being 3, so 3 here, predecessor again U. For X, link cost being 5 and predecessor U. And yeah, 7U, 3U, 5U, infinite, infinite. Okay, so we just finished initialization phase of the Dijkstra algorithm on the example. Entering the looping phase. First thing we do in the looping phase is what? To find the I that is not yet in M prime such that the shortest distance to I is the minimum. And we add that I to M prime. Alright, so let's go over the DI. Okay. 7, 3, 5, infinite, infinite. Which one is the minimum? 3 here is the minimum. Therefore, I is W this time. And we'll include I into the M prime set. That is why. Next, we see U and W both in the M prime set. And then, we can now do the second thing we do in the loop. We'll update the minimum cost. And we're going to do this for all the nodes adjacent to, what is the I being added there? W, right? So we'll go over all the nodes adjacent to W, okay? And that is now already in M prime. So who are the nodes adjacent to W? X, Y, V, Y disconnected, okay? Because there's one link here. And U, all right? But you know what? U is already in the M prime set, so let's remove this. So there are just 3 nodes, okay? It can potentially be J, and we need to update the minimum distance and the predecessor node. So what we'll be doing here is to exploit W here, okay, as a hopping node. So V here, okay, there's another path, right? Originally, we had this direct link. But now, there's an alternative path through W, which is what? 3 plus 3. Okay? The minimum distance to W plus the link cost between V and W. And that is how much? 6. Is 6 better than the existing minimum distance to W? Existing minimum distance to W, existing minimum distance to V is 7. And that is indeed better. Okay, so 6. And in case it's better, the new path is better, we'll set the predecessor to the new node we are hopping through. So V is now taking W as the predecessor, and the cost, minimum cost from the source, is only 6. Second neighbor, Y. Previously, dy infinite. Currently, if we use W as a hopping node, 3 plus the link cost between W, Y, 8. Together, 11. Obviously better than infinite. And the predecessor is what? W. Third neighbor of W, X. Exploiting W as the platform, hopping, and then adding the link cost between X and W, that is 7. Is 7 better than dx? Dx was 5. 7, oh, yeah, in X's case, not better, so we'll keep 5. Z not being connected, it will remain the same, so remaining infinite. And therefore, we should see 6W here, 5U here, 11W here, and infinite here. So what do we do next? Well, we're in the loop, and we are not in the condition to end the loop yet, so we're not yet done. We have only U and W in M prime. Okay, there are more nodes. Okay, we could consider adding to the M prime set. And the way we add to the M prime set is to pick I such that di is the minimum. So dv6, dx 5, dy 11, dz infinity, which one is the minimum? Yeah, x is the one we're picking this time. So we'll include x into the M prime set. And we see there, x here is the I. So we'll be examining all the nodes adjacent to x next. So x is here. The adjacent nodes include u, w, y, and z. But you see, yeah, we'll be going over all the nodes adjacent to y, but not yet in M prime. U and w are already in M prime, so we will not be updating du, not updating dw. So let's update dy. The way to do it is to follow the formula. What is dy now? The current cost, 11. What is the newly discovered path cost? What is the new path? Well, one can actually go to x and then using x as a hopping platform to reach y. And the total cost is 5 plus 7. That is 12. This time, the new path is actually not better than the existing path. So we keep 11W here. The other neighbor, Z. Okay, what is the current cost? Infinite. So infinite here. Cost to x is 5. And the link cost from x to z, 9. So the new path discovered is 14. And the predecessor is x, which is better than infinite. So 14, x here. Now, v is not even a neighbor of x, so we'll just not update dv and pv at all. So, and that's why we see 6w here, 11w here, and 14x here. So this is the second iteration in the loop. And next, pick I again with the minimum di. 6, 11, 14. Therefore, we include this time v into the M prime set. So 6 here included, v included to the M prime set. And therefore, the I is v. So I here. We'll go over all the adjacent nodes of v, which includes u, w, and y. And that's now already in M prime, so that includes u and w. The only node that we need to actually update the d for is y. So we'll be updating dy. Existing dy, 11, right here. So if v here is the hopping platform, the cost to go to v, the cost to go to v is actually what? 6, okay, through w. The link cost from v to y is what? 4. So 6 plus 4, 10. Is 10 better than 11? Yes, it is. So let's update it. And this time the predecessor is what? V. Okay, so that is also saying This pass here was no longer good, and this is actually a shorter path. Now Z is not directly adjacent to V, so we just leave this entry down. That is why we see 10V and 11X.
All right. I know that you guys probably pick it up already because many of you are already answering quizzes. So why don't we just jump to the quiz, because the rest of the iterations are actually repeating itself. Okay, so now let's go to the quizzes. Let me transition to the quiz sites. Just give me a second. All right. You see here, this is quiz 34. You see that here's another example, isn't it? A different network. U, V, X, W, Y, Z, 6 nodes. And you know already the precondition is that we'll start thinking U is the source. So we are computing, we're computing assuming that U is the source. So the endpoint is initialized with U in the set. Okay, and this is the initialization pseudocode, and I'm asking you to fill these values, okay, of step 0. All right. And you know what? Quiz 34 and 35 are actually related. Let me just tell you ahead of time. Quiz 35 is to continue. So you kind of see the answer already. Yeah. Quiz 35 is to continue into step 1 and develop the entries here, okay, for step 1. So you need to be careful which is the next node to include here into M prime. Okay. So those are 34 and 35. Okay. What we will do now is to take a break, because it's time to take a break. And after the break, we'll come back to see how you guys are doing with the quiz 34 and 5. It's now 2:07 and we'll try to come back to the class at 2:17. Yeah, finally, Jiahong detected that you guys need to answer what is the new M prime. Right, So, Kevin? Wei Yao, are you okay, so Wei Yao, Wei Yao. Yeah, M prime. Same for James. Yeah, same for team 3, Shu Wei. Same for double jelly. Yeah. So this one is perfect. There we go. Very good. Ah, okay. Ah, okay. See, I'm a little bit confused between the two of you. Kevin Yao and Gao Wei Yao. There you go, Ethan. Very good. Tai Changling, very well. Let's see, team 4. Good, so Boyshun answer for quiz 34 and you answer for quiz 35. Nice. Very good. So we pick X to include into M prime, right, in the first step. Very good. Kevin here. UX, very good. Okay, Hongshin here for team 1. Very good. Shiwei, okay, including X. 2U for X. Neo for X and then 2X. Very good. 2 cows. Interesting. Jin Cai. Yeah, so UX is the N prime, 2U for X, Neo, infinite and Neo. Very good. Oh, okay. All right. perfect. All right, so let's come back to the lecture. I guess you guys are doing very well. Perhaps it's because how you guys are selected into the department. So very good at following Sudoku, math-oriented problem. Yeah. So here, to challenge you more, how about step 2? Who's the next node to include? Ah, according to quiz 35's answer. It seems that no V and no Y, the cos are both 2. So this is a bonus question. Okay, you don't have to answer it, but let me give you like 5 minutes of time to work on it. Say, what do you think row number 2, step number 2 is gonna look like? Okay, actually Polly doesn't know what the answer is, so let me do it also myself. Okay, so double jelly here thinks that there are two, right? Having the pass cost being two. So there are two of these nodes with minimum pass being two. Very good. Therefore, you need to tie break. Yes. Yeah, and the double jelly is suggesting the tie break rule is alphabetic order. Why not? And James is suggesting that we'll see which one is the minimum cost next node first, isn't it? And V in step 0 is already the minimum cost. So why not? Mm-hmm. So James's way of tie breaking is also fine. Oh, okay, let's see what's there from Slack. Okay, Wei Yao is saying, suppose it's alphabetic order, then it will be UXV and then 4x and then 2x and then infinite. Very good. So can anyone share in case if you choose Y to be the winner of the tie break? So for example, reverse alphabetic order. So what will be the outcome then? Then M prime will be UXY. So Wei Yao is right if it's alphabetic order. Mm-hmm. Okay, so James is also right about, yeah, so this quiz is called the quiz bonus. So there's no specific number for it. So it's week 15 quiz bonus. So James here, yeah, so taking alphabetic order, or James was proposing whichever being discovered. So what about Y? What if we choose Y? What if the tie break mechanism chooses Y? Oh, there. Oh, wow, okay. Pei is actually showing in either case. Okay, very good. Nicely done. So if we choose Y, then it will be 2U, 3Y, wait, oh, it is, yeah, because you need to update the W entry, there's a better route, and 4Y, very good. Because Z now has also discovered a way to go to U, isn't it? Which is through Y, and the cost is 4. Okay, and this we know. Many of you had already worked on that. Now if we take Y, it is 2U, 3Y, and 4Y. 2U, 3Y, 4Y. Very good. Angela, 2, 3, 4. Very good. Hi. Great. So let's see. Changlin here says also 2U, 4x, and 2x. Very good. Okay, more of you answered. What if we take Y? Yeah. Okay, so you do random. Okay, so there's another way of breaking the tie, right? What if it's randomly choosing one? And both is fine. So if you choose Y, then yeah, so you ended up with this. So you see that the derivation table might be a little bit different in case there are equal lengths nodes that you can pick from. So the intermediate steps might look a little bit different, but the eventual shortest path, the cost will be the same. Even though the previous hop might also be a little bit different, because it depends on which one you include first to n prime, isn't it? So the path could still be very different, but the cost would be always minimal. Okay, Jiahong here. Very good. So if we pick Y, indeed. Good. So you guys are really keen in algorithmic or mathematical derivations. Okay. So the next video is just to go over this example that we went through in quiz and to its completion, just for the sake of having a closure.
Let's walk through the second example, which is illustrated right here. Once again, U is the source, and step number 1 in the initialization is to include the source into the n prime set, and that is why you see U being here. Now, step number 2, that is to what? To go over all the nodes and see if it's adjacent to A. If it does, then we do this. Set the minimum distance to the node to the link cost between the source and the node, and set the predecessor to the source. So who are the nodes adjacent to the source U? So we do have V and W and X here, right? V connected to U, W connected to U, and X connected to U. And therefore, dV should be the link cost of UV to dW, link cost of UW, dx, link cost of UX. The predecessor is always the source, therefore U, U, and U. For these two nodes who are not adjacent to U, we write infinite, okay, which is the else here. Set the distance to those nodes, infinite. And to be precise, the predecessor for those nodes will be then also nil. So 2U, 5U, 1U, infinite, infinite. So therefore, okay, to fill in the first row, step 0, 2U, 5U, 1U, infinite, infinite. Now we then enter the looping phase. Okay, in the looping phase, what we do first is to find a node that is not yet in n prime, but okay, di is the minimum. So what di we have? We have 2, we have 5, we have 1, infinite, infinite. Which one is the minimum? Yeah, this one here. Therefore, what do? We include x, okay, into the n prime. And then we move on to the second step in the looping phase, which is to update the minimum distance to these j's that are adjacent to I, which is x, okay, in this iteration, and not yet in n prime. So let's find out the j first. X here is the I. So u, v, w, y are nodes adjacent to x, but u is already in n prime, so we'll discount u. So we just need to walk through v, w, and y and update the distance to v, w, y. So let's start from v. Okay, the old dv was 2, so, which is this entry here. Now we need to find out the di plus cij. So di is this, being 1. Cij, so I is x, j is now v, so the link cost is 2. So the new dv there is 3. Is 3 better than 2? Well, not quite. So we'll just leave the entry as is, okay, for column V. Second neighbor here, second j is w. Okay, so original dw, 5. So 5 here. These are the old ones for V. So what about di plus Cij? Di is still 1, okay, and Cij is what? 3 this time. Okay, so in a way, this new path they just discovered, the cos is 4. Is 4 better than 5? It is, therefore. Okay. We write 4 here, and the predecessor is now the I. Because this new path, okay, for destination W, the previous node is X. What about Y? The new path being discovered is this one over here. So 1 plus 1, which is 2. And the O, okay, O dy is what? Ooh, infinite. So 2 is definitely much better, right? And the predecessor, again, being X. Z is not connected, so we'll just, write the entry down. Okay, so we have 2u, 4x, 2x, and infinity. That should feel, the second row here. 2u, 4x, 2x, and infinity. And that completes step 1. And that takes us back, okay, to the second iteration of the loop, where we find another I, where the di is the minimum. But in this case, what we're seeing here is, 2, 4, 2. We do have a tie, so we need to break the tie by picking one of these. So let's suppose that we pick y, and therefore we include y into the n prime. So y here is the I for the second iteration. So again, we walk through all the nodes adjacent to y, which includes x, w, and z. But these nodes cannot be in n prime yet. Let's see, x is already in n prime, so let's exclude that. And then consider only w and z. So let's see, what was the dw currently? 2. What is the new path we are exploiting here? It's this one here, isn't it? Okay, so 2 plus 1 being 3. Is 3 smaller than 4? Yes, 3. Okay, and now the predecessor to go to destination W is y. Nice. Okay, yet another shorter path to W. For z, okay, the old cost, infinite. Okay, exciting. Because the new path here, 2 plus 2, 4, is obviously better than infinite. So we should be seeing what? Okay, 3y, 4y being added. V not being directly connected to y, we'll just write the existing entry down. So 2u, 3y, and 4y should fill the third row. Okay, complete step number 2. And again, we come back to the step 1 of the looping phase, and we pick the node that has the smallest d. This time, it will be v to be included here. Okay. And to complete the 4th row, we take the second step in the looping phase. Go over oj connected to I, and I is this time v. So where's v? Right here. Right. So all the nodes adjacent to v, but not connected, not yet in the n prime. So u and x already in n prime. So let's exclude those. So the only node remaining is just w. All right. So dw currently 3. So what is the new path we're exploiting here? This one here. Okay, so cost being 2, link VW is 3. So total cost for the new path is 5. Is it better than 3? No. So we just write down the same thing. Okay. Z is not directly adjacent. Let's see. B and Y already taken. So just 2 entries, 3y and 4y for W and Z. And that should complete 3y, 4y. Yet another row. So we're again in step 1 in the looping phase. So W is obviously the next one to include into the n prime set. And W is right here. For all the nodes adjacent to W, V, X, U, Y, Z. Well, actually, all of them connected to W. But you know what? U, V, X, Y are already in the n prime set. So it's just Z remaining. We need to see if the existing cause is better than the newly discovered past cause. Newly discovered past is W, and the cause was 3, predecessor of W was Y, so it's this past here. So 3 plus 5, that is 8. Is 8 better than 4? Well, not. So 4y remain here, and that fills up the last row. And next is to what? Include z into the n prime set. And that iteration for step 2 is trivial because no nodes is remaining there and not in n prime. And so this is the complete link state derivation table, okay, for the second example. Now, let's try to build the Dijkstra shortest path tree again, right? So let's go over all the possible destinations. From z, the predecessor is what? Y. Y's predecessor is x. So x's predecessor, u. Okay. So then we don't have to do it again for xy, okay, because they're already in the tree. Predecessor of w being y, so right here. Okay. B's predecessor, yeah, simply u. So this here, okay, is the shortest path tree built from the Dijkstra's algorithm. And that's what you see. Yeah, the shortest path tree being built from Dijkstra. The forwarding table that we need to install in router U is this. For destination B, yeah, whatever the shortest path indicates, this link here between UV. But for all the rest of the destinations, yeah, this other link, UX link. And this is how, okay, we come up with the forwarding table after running the routing algorithm. Okay, so using Dijkstra, let's build the shortest path tree. And it's clear, okay, for the destination over this branch of the tree, take UV. For all the destination over this branch of the tree, take link UX.
So that's Dijkstra. And you will see next week a real internet routing protocol called OSPF is built based on the link state routing. Okay. Now there are actually a couple issues. So next video is gonna discuss the time complexity of doing the Dijkstra computation, as well as a very weird situation called oscillation, route oscillation. If we use, for example, the traffic volume, okay, as a way to weight the links. So when you're doing the examples, right, there's always this link cost. If the link cost is based on the amount of traffic going through the link, then you might have this route oscillation problem. Let's hear it out.
Now with the two examples walked through, you see the Dijkstra's algorithm, although look a bit cryptic, okay, at the beginning, it's in fact quite straightforward. Initialization phase, 2 steps. Looping phase, 2 steps. Looping phase is the one that we take multiple iterations, we spend more time with. So that is going to bound the complexity of the Dijkstra algorithm. And within the looping phase in each iteration, which of the steps is taking the most time? Yeah, the second step. Inside the second step, we're actually checking all nodes J. Okay, that is adjacent to the node we just added into N prime. Okay. And inside, okay, each iteration in the inner for loop, okay, what we do is this, the min operation. And this is in fact to compare the value of the current shortest path to the newly discovered path, right? So D to I plus the link cost between ij. So it's a comparison between this value and this value. So you have the looping phase, and inside there's an inner loop, okay, that is doing a lot of these value comparisons. Now, if we consider a fully connected network, that is the worst case for Dijkstra algorithm. Inside the network, there are n nodes. Okay. In the first iteration, so only the source is in the n prime. How many j's, okay, is connected to the source? Yeah, it's fully connected. Therefore, n minus 1 nodes, okay, they will all be j, and we'll need to do mean for each of these j. First iteration, we'll need to do n-1 comparison. Second iteration, how many? Because there's one more node being included into n prime, so number of j in the second iteration, only n-2. Third iteration, and we can go on until, okay, the second last iteration, we have only one node remaining connecting to the new node being added to the n prime. In the last iteration, yeah, the second step is not going to be called, okay, because there's no j remaining. So if we add all these together, okay, this is the number of comparisons. N multiplying n-1 divided by 2. And this is in the scale of n squared, big O n squared. So big O here is actually to say that the Dijkstra algorithm in the worst case runs in the scale, okay, of n squared. That means, okay, the time complexity, the growing trend of Dijkstra algorithm is this. When n approaches where the network goes really big, okay, the time requirement goes in this trend, like an n squared curve. Now, if it's only big O n, the curve is linear, okay, a straight line, sorry, the line is not very straight here. Now, there's an implementation, okay, available for Dijkstra algorithm, such that we could do away with only n log n. Now, this is better than n squared. So again, n is here, n squared growing really fast here, and n log n is actually kind of in between. Faster than the pseudocode we've investigated, and better than a linear algorithm. So, nice to have an efficient implementation, even though the original Dijkstra algorithm is not so good. There's one very special issue with link state routing that's called the path oscillation problem. And it happens when we set the link cost dynamically based on the amount of traffic going on the link at the time. Yeah, let me explain using an example. Okay, so we have 4 nodes in the example, A, B, C, and D. A is the traffic sink. Okay, all traffic goes to A. B, C, D are traffic sources. A generates one portion of the traffic and send it over past BA. E generates E portion of the traffic. E here is a very small amount, much smaller than 1. And C is taking the CBA path to send traffic to A. D generates also one portion of the traffic and it's taking past DA to send to destination A. And at this point, we need to update the link cost based on the traffic going on the link. So for link DA, amount of traffic is one portion. For link BA, amount of traffic is what? One portion plus the E portion from C. So total cost, 1 plus E. The cost for link CB, amount of E traffic from C only. You see also here, okay, this direction, BC, there's no traffic, therefore link cost is 0. Similarly for AB, similarly for AD, and similarly here for both direction in link CD. So we finish updating the link cost. After a while, link state routing is going to trigger Dijkstra algorithm running again. As I described, link state routing is a dynamic routing algorithm. We do periodic update, and sometimes we use also, okay, network events to trigger recomputation of the routes. Link state routing there does periodic recomputation. Okay, it's going to recompute the routes based on the link cost now. So let's see. B here, we'll see 2 possible paths to go to A, right? One is to go counterclockwise to A, the other clockwise to A. So this direction here, the cost is what? 1 plus E. because there's only one link and the link cost is 1 plus E. If we take this other path, B, C, D, A, yeah, the path cost is the sum of the link costs, 0 plus 0 plus 1. Okay, so if we take the clockwise path, okay, to go from B to A, cost is only 1. And this is 1 plus E, therefore B is going to choose to go this way to send traffic to A. C, also see two possible paths. Okay, if we take this direction, cost is E plus 1 plus E, and that is 1 plus 2E. The other direction, cost is 0 plus 1, therefore 1. And therefore, C will choose to go also clockwise to send traffic to A. Similarly, D sees also two paths. Okay. This direction here, cost is 1. This direction, 0 plus E plus 2 plus E, 1 plus E. So altogether, 1 plus 2E. So still, okay, this direction better. So D is also going to take the clockwise path, okay, the same path to A. So after the route computation complete, you see B, C, D all change to send traffic clockwise. And then we need to update the link cost again, right? So given the previous cost, we come up with the new routes, and we will then, okay, update the link cost, and we come to the new cost again. What is the new cost now? Okay, on link BC, yeah, there's only one portion of the traffic. On link CD, yeah, 1 plus E. On link DA, 2 plus E. And that is why we see 1 plus E, 2 plus E, and all the rest of the links, 0. Once we update the link cost, after the next period that the Dijkstra algorithm is triggered, we compute new routes. So B will then try to see the cost to go this direction and the cost to go the other direction. The cost going counterclockwise is now 0. Cost going clockwise is now 1 plus 1 plus E plus 2 plus E. That's 4 plus 2E. So dominantly, BA is the better path. C's cost going this direction, 0 plus 0, cost is 0. The cost of the other direction, 1 plus E, 2 plus E, 3 plus 2E. So C is going to switch going this direction to send the traffic. What about D? Going this direction, 0 plus 0 plus 0. Going this direction, 2 plus E. So D is going to switch for the first time to go counterclockwise. And that's why in the next moment, you see traffic begin to change direction completely. Okay? From all clockwise, okay, one period before, to counterclockwise the next period. So given these new costs, we calculate the new routes all going counterclockwise, and we update the new costs again based on the traffic. DC is now 1. CB is now 1 plus E. And BA now 2 plus E. And that is what you see here. 1 plus E, and 2 plus E. As a result, B sees this path costs 0. This path costs 2 plus E. B switch the other direction. C sees this path, really high, 3 plus 2E. And this other direction, 0. D, this direction, 0. This direction, super bad, 4 plus 2E. So all of them would switch back like this. And the link cost gets updated again. 1 on this link, 1 plus E on this link, and 2 plus E on this link. which is identical to 2 periods before. Okay? And you see the next period is going to be like, yeah, the previous period. And the traffic is going to oscillate infinitely, right? Clockwise, counterclockwise, clockwise, counterclockwise. So that is the path oscillation problem if we set link cost dynamically in link state routing. Okay, that's running the very straightforward Dijkstra algorithm. Just be careful here.
All right, so the time complexity was one of the major issues with Dijkstra. There is a remedy, so there's a more efficient algorithm running in n log n. Oscillation issue is happening only when the link cost is dynamically assigned based on traffic. So we just don't assign link cost based on traffic going on the link. But the question is, how do we assign link costs, right, on the internet? Think about it. As we wrap things up, and that's here just this short summary clip.
To put simply, link state routing works this way. Each router implements the routing algorithm. It's going to wait until the total information of the network is in place. Then it calls the Dijkstra algorithm. At the end of the calculation, we get the least cost path from this router to every destination possible in the world. So that is essentially the shortest path tree. Now that router being the root of the shortest path tree, we'll see there are multiple branches out to the rest of the world. Taking one branch, it gives you the shortest path to a certain set of destinations, another branch to another set of destinations, yet another branch to yet another set of destinations. And so, from the tree structure, okay, we can construct the forwarding table, and that is how the forwarding table is calculated in the control plane. Next is just to install it into the data plane. Now, the only part I'm going really quick without mentioning much is this: how we get the total network information so we could apply the Dijkstra algorithm in the first place. That is done through this link state broadcast. Each node, okay, in the network is going to generate link state report based on very local information. That includes the ID of the node itself, the ID of the immediate neighbors, and the cost, okay, on the link to these immediate neighbors. Okay, so these are the local information. Node, the neighboring nodes, and the link cost to the neighboring nodes. So all these local information is going to be in the link state report coming from the node. This link state report is going to be broadcasted, meaning, okay, going out through the entire network, being received by all other nodes. So all nodes eventually will receive link state reports from every other node. And these link state reports from every other nodes, including the node's local information, is going to be used to restore, okay, the total network. Let me give you an example to illustrate how that is done. We have a very simple network here, only 4 nodes. Okay, you see, U connects to V, U connects to W, U connects to X. Okay, so if we are node U, okay, and generating node U's link state report, it's going to contain this: the ID of the node itself. And there are 3 neighboring nodes, V, W, X, and the cost on the link to these nodes. 5, 3, 7. So U to V, link cost 5. U to W, link cost 3. U to X, link cost 7. Similarly, V is going to generate its link state report, which is going to contain only one entry. It connects to U, link cost 5. The link state report from W should look like this: 2 neighbors, U and X, cost being 3 and 2. Link state report from X is contained 2 entries, U and W, link cost 7 and 2. So each of these nodes, U, V, W, X, is going to broadcast their link state report, and every node in the network is going to receive its own local information and every other node's link state report. Therefore, no U here is going to receive the link state reports from V, W, and X, which we know already look like this. The way to restore the network topology is this. Okay. No U knows the local information. It connects to V. It connects to W. It connects to X. Cos is 5, phi 7. Now, seeing no V's link state report, it knows that V and U is connected. Cos is 5. V, U, I'm U, so I know. Okay, and the cos is 5. W's report is going to tell, okay, the cos to U is 3, which you already know. Oh, W is also connected to X with link cos 2. So W connect to X link cos 2. X report says I connect to U, so X connect to U, you already know. X reports also that it's connecting to W link cos 2, which you already have. And you now manage to reconstruct the total network information from receiving link state reports from all the nodes in the network. And it's contributing also so that other nodes receiving U's link state reports can also reconstruct the total network. So you see this one here, U connecting to VWX. Yeah, isomorphic, okay, of the network there. So that was the last piece of the puzzle, link state routing. Other problems you see here. Now you know a little bit about the link state broadcast. Yeah, some of you might see this. These link state broadcasts, it's going to travel the entire network. And it's coming from every router, right? So you have n copies of these packets going to n nodes. The bandwidth consumption is again at this scale. And to store the topology information in the router, right? So we discussed the complexity of Dijkstra algorithm. We only talk about the time complexity. We have not yet talked about the space complexity. It's also huge, right? In the worst case, you have n nodes fully connected to every other node. Then you have what? N squared number of links. You need to store costs, okay, for all these links. Ugh. Not very scalable when the network goes big, when n goes large.
Yeah, and that actually takes us to the next topic. Good that we didn't need to spend all that much time for the quiz 34 and 35, so we can actually break open distance vector today. Before we do that, then I want to draw your attention to one of the suggestions students suggesting that we break the tie, selecting the next node to include to n prime. So I think James proposed that we would take the node that would that was the lowest cost already and earlier. Okay, so it seems that V in the example for the quiz is the one, okay, that comes to cost 2 earlier. So I think Double Jelly here is agreeing, okay, and saying that that might be a little bit better than just using alphabetic order. Okay, why? Because potentially the number of hops you take is also lower, okay, and if you take a lower number of hops, then it minimizes these type of delay, processing delay in the router and potential queuing delay in the router. Okay, so interesting idea, isn't it? Yeah, so we were talking about link cost. Okay, if we cannot use traffic volume, what will be a good link cost to set? Okay, so think about that as poly moving to distance vector. You see link state routing, even though time complexity can be a little bit better, even though oscillation issue can be addressed by using other type of metrics to assign link cost, but it's got memory complexity issue. It's got traffic complexity issue. think about it. If the network is huge, when n goes really big, yeah, that's not gonna scale, especially given the size of the internet now. Okay, the size of the network in case we are running Dijkstra routing for the entire internet. That sounded really scary, isn't it? Yeah, and that's why we had distance vector routing. Okay, so the video is very short. That's open distance vector.
So you see, link state routing works fairly well for small networks where n is small. For access network, institutional network, local area network, it might be okay. But for the entire internet's backbone, there's no way we use link state routing. And that takes us to the second routing algorithm, okay, distance vector in the chapter. So distance vector routing is exactly here to address the space complexity, to address the message exchange complexity in link state routing. If you think about it, the reason that this link state routing takes so much space, requires sending of so many messages, is because in order for Dijkstra algorithm to run, we need the total network information. So the question to ask is this: can we come up with a path? Can we discover best paths, best routes without knowing the global information? You know what? It's possible. We just need to be a bit patient though. Okay? So Polly here might have two neighbors, Alice and Bob. Bob and Alice do not know each other. Okay? There's no path existing from Bob to Alice. But if Polly shares how Polly knows Alice to Bob, then Bob will know that there's one way, right, to reach Alice, which is through Polly. So I tell my neighbors, and you tell yours, okay, about what you know. Gradually, okay, the network, okay, will spread the good news out and discovering a path, a route, okay, to every other node in the network. That is the general idea of distance vector.
All right. So you get the rough idea. So let's continue on with that rough idea with quiz 36 and exercise it. Okay. So quiz 36 is asking, suppose you are router X, so you need to pretend that you're a router. And you need to send data to W. So this is the network. You are X right here. You need to send data somehow to this guy, W, far away. And we don't know exactly what's in here. All right. Now, let's suppose router Y here tells you, I know a way to W, as opposed to router Z here says, I have no idea. So, between Y and Z, which one would you prefer passing the data to so that you have a higher chance of reaching W? Oh, there. Okay, Wei Yao, representing Team 11, says Y. Since Y said he knows the path, and the cost passing to Y is also lower. Yeah, because in Z's case, right, Z says I had no idea, so the cost is what? Infinite. Very good. So that's the idea, right? Given these information from your neighbor, you make the best judgment, and that's essentially what distance vector is doing. And you can do routing without knowing everyone in the network. Okay, you just need to know your neighbor and hope that your neighbors are informative. All right. Well, consider this next one, okay, which is a little bit more complex. Consider this case. Good. Yeah, answers for quiz 36 are flying in. 37 is not more difficult. Look at this. You're still router X. So you're still here, router X. Oh, oopsie. Same, you need to send, oh, shoot. Yeah, same, you need to send data to W. And this time, Y here says, okay, I know a way to W. Okay, X, Mr. X, I know a way to W. And hey, through me, the cost is 2. Z here says, okay, I also know a way to W this time. But the cost, if you send data through me, my cost to W is 10. Okay, U as X here. Okay, you know the cost to Y is 2. And 2 is saying that this is going to be 2. X here to Z, the cost is 7 because these are directly adjacent link. You know the link cost. And Z says, oh, okay, so if I need to forward the traffic for you, the cost will be 10. Now, which way? Okay, is it through Y or through Z you would prefer sending the data, and why? Okay, let's go to 37. Oh, Jiahong now beats Wei Yao. Okay, Jiahong says, why? Since the cost to W is less than Z, what Z has told, isn't it? Okay. So according to Z, the total cost will be what? 17. According to Y, the total cost is what? 4. But now, hey, it's a little bit tricky. I'm pretty sure that some of you also detected the problem here with distance vector. In link state, hey, if you are in link state, what is the best way? Okay, fine, link state is still 4, right? But you see also, between Z and W, Z says, the cost was 10, okay? And X will be thinking that the total cost is 7 plus 10, 17. But the thing is that from X to W through Z, it can still be somewhat better, right? If it's going through Z, which is to go here. In link state, you'll be able to see there's an alternative way to Z by sending data this way and then to W. And the cost there is what? Yeah, 13. Okay. Consider this case. What if, okay, the cost here is 1, okay, and the cost here is 7. And the cost here is still 2. Which one do you choose to forward traffic? Well, you see, right? The overall cost, if we send it through Z, is 11. Through Y is 9. So you probably send it this way. Okay, in distance vector, because you only need to trust, all you can do is to trust what the neighbors told you. Okay, but look at this. This is 2. I forgot what was the setting. Yeah, I think I changed it to 1, and I changed this to something like 7. And this is still 10. Okay, yeah. So overall this is 9, and this is 11. Okay. But what about this? This is 1, 1, 2, 4. Okay. If you're using link state, you're always finding the shortest path. With distance vector, you are limited by what your neighbors know. Okay. But next on Thursday you will hear the overall distance vector routing algorithm, where you will see, even though for the short time being that you don't get to send data using the optimal path, but over some time, okay, once this good news propagates throughout the network, everyone will still converge to the shortest path. Oh, you can't see what I'm drawing, sorry. I see. Yeah, sorry, okay. This is what I was intended to. Okay, so I say you can only imagine. Yeah, so I need to come back to the previous slide here. Okay, quiz 37. Good that you let me know. So here's what I was trying to do. Let me change the link cost between xz to 1. So 7 is now 1. And that's changed link cost xy to 7. 2 to 7. And change the distance from y to w. No, so what y tells you is the same, 2. What z tells you, being x, is same, 10. Okay, so in this setting, overall cost, if you pass it to z, you'll be thinking that it will be 1 plus 10, and therefore you have 11. And up here, through the path that's going through y, then it's 7 plus 2. Total is 9. So between the two, you will be sending traffic x, y, and w. But in this configuration, the best way is in fact x through z, z to y, and finally to w. If you know, if you're running link state routing, yeah, then you know everything. You know there's, oh, interesting, there's a link here, cost being y. If you send it this way to y, it will be better. Instead of you standing here, you only see your connectivity to y costs you 2. Okay, so I hope that illustrates the main differences between link state and distance vector. In distance vector, at any point in time, you might not be able to send traffic with the minimum cost path. But in link state, after the computation is done, you are always sending data using a minimum cost path. But in distance vector, on Thursday, you'll hear the algorithm will be spreading the news about how we know each other. For example, y knows w this way, z knows w another way, but as we are passing these information, for example, z passing its connectivity to the rest of the internet to y, then between y and z, they will discover, oh, the link cost between them is 1. Okay, and when y tells x further, then x will know there's a better way, x, z, y, before y passing the data further to w. Okay, so it's iterative. It will take some time until everyone knows what's the best way to send to a particular destination. Okay, I hope that communicates the main difference between the two routing algorithms. All right, and that's all for this today. Okay, I'll see you again on Thursday. Let me see. Any other question? We can actually, I can't. The counterclockwise and clockwise and etc. Okay, Yode, I hope that you finally see it. Shouldn't z know that the distance to w is 3 if passing through y? Shouldn't z know? That's a very good point. So Shiwei, again, z might not know better unless y tells z. So at some point in time, y might not know all that well. Okay, so the information y tells z might be a little bit limited. So z is still under the picture that the best way is somehow between z and w. In the example earlier, 10. Good. So I hope the last part, okay, I'm drawing is a little bit more clear. But in the worst case, Thursday, we'll introduce distance vector algorithm. You'll see. We'll not actually know what's optimum temporally. On Thursday you will see. I think, yeah, there will also be quiz. In fact, distance vector is not that intuitive. Okay, to derive the path, it's a little bit more complicated, and it's usually harder for you guys to pick up. So quiz 34 and 35, too easy, obviously. Okay, quiz 30A will be hard. In fact, quiz 39 is still related to distance vector. It's super hard. Okay, so if you're looking forward to challenges, Thursday we'll be going through quiz 38. Next week, Tuesday, we'll then have time to go over quiz 39. Good, so see you on Thursday. And then I'll come to quiz 36 and 39's Slack space and check you guys' answer. Let's see, 37. Yeah. Y knows a lower cost path than Z. Exactly. Y. Wait. Wait. Okay, I need to start from the beginning. Yeah, I guess you guys were. Yeah, given the scenario, y there total cost 4, right? Shorter, way shorter than 17. Oh, feel free to leave. Okay, bye. Definitely. Okay. Exactly. Very good. Two versus 17, very good. Team 3, very good. Greedy choice, definitely. There we go. Yichen. Choosing Y because the cost is lower. Very well done. However, here the cost through Y is lower, obviously. CI here says XY ... W is 4, therefore lower. Very good. Junyuan, Lin Junyuan. Oh, okay, I know who you are. Why? Because, yeah, that way is minimum. Okay, good. 37 should be really obvious, isn't it? Why? Since Y, even if Y doesn't work, you could still go to Z with just okay. Ah, okay. Interesting. Very interesting. Alright, Johnny, very good. One can still go to Z with just cos of 1, but this is again assuming that you're link state routing. Therefore, you know the cost between Y and Z is 1. Why? Because Y is higher confidence? Good. Hongxuan will choose Y because you may not know, right? Exactly. You may not know whether Z knows the way to W. Very good. Alright, same here. Good. Great. I'll pass the data to Y. Very good. at least y knows the way to w. Very good, because z's way is uncertain. Okay. Very good. Y is already. Good. I see this is the easier of the two quizzes because y knows the way to exactly. Oh wait. And same for team 19. All right, good. So let me end the video session. Finally.